Hello and welcome to lecture number 9. So in this lecture, we would extend our concepts that we learned for one-dimensional wave equation. We are going to extend into two dimension in the form of a vibrating membrane. So therefore, whatever we have learned in chapter 7 and 8, the knowledge would come and help us. So therefore, what we assume is we have a two-dimensional membrane. Okay, so this is x and this is y, and it is clamped along x-axis at a length a, and it is clamped along y-axis at a length b. So it's all four sides are clamped along the perimeters. So therefore, if the membrane starts to vibrate, it will obey the classical two-dimensional equation. So in this case, it can be written as uxx plus uyy is equal to 1 over v square utt. Alright, where u would now be the function of both the two dimensions, that is x and y, as well as t. So x, y and t are now independent variable. Okay, so we all know that u is here the amplitude function. Therefore, we are going to write once again the boundary conditions, because these conditions are very important to find out the specific solutions. So the boundary condition says that u at x is equal to 0 at any value of y at any value of t is equal to the same thing at x is equal to a, any value of y and any value of t is equal to 0. Alright, and same thing goes for the other way, that is for any value of x and t, if it fulfills this condition, again it becomes 0. Alright, so now we are going to solve this partial differential equation. Alright, so then how we do that? So again, by the same separation method of separation of variables, so we can assume that let u, x, y and t can be expressed as a function of x and y, which is independent of time, and multiplied by the function of time t. So it's a product of two different independent functions. So therefore, so if we call this as equation 1, so we can write that equation 1 can be written as we can directly write this over here. So we can write it like this. So this would be as a common factor, and del 2f del x2 plus del 2f del y2. I'm not writing all the terms because f means function of x and y, so I'm not writing it all the time, is equal to 1 over v square multiplied by f xy. So we just, let's write the f like that, and therefore del t2. Okay, so this is the next step we can easily write. And then, or of course, now what we are going to do, we need to separate the variables. So we need to divide both sides by this product of f and t. So divide both sides by product of f and t. We get here 1 over f, all right, del 2f del x2 plus del 2f del y2 is equal to 1 over v square and then 1 over t del 2t del t2, this one. Okay, so once again we see that we have arrived at the same situation like before. So this part is a function of x and y, and this part is purely a function of time. Okay, So one independent function is equal to another independent function, consists of two independent variables. Now this can only be happen when both of these become equal to a constant. Now from our previous knowledge that we saw that it is wise to assume that the constant is equal to a negative value. So we can directly equate it as of negative beta squared. So we are all familiar with this part, okay? So now we are going to break this entire set of equation into several or three smaller equations. So let's continue doing that. So from the last equation, we derive those two sets of equations. So this is the equation for the time, and we see now individually equation 2 becomes an ordinary differential equation, of course second order, and we all can recognize this pattern. So therefore we can equate v beta with omega, that is the angular velocity. But this equation 3, it is still a partial differential equation. So again we have to separate the variables because f contains the partial derivatives, like these are all partial derivatives. So you have to separate the variable and we have to make them ordinary differential equations in order to solve it. So how do we solve it? So again we can solve it by let fxy is equal to, once again, product of two independent function containing independent variables x and y. So the moment we write that, we have to define our boundary conditions. So I'm writing in short the boundary conditions. So at x is equal to 0 is equal to x is equal to a is equal to 0, and at y b is equal to 0 or is equal to b is equal to 0. So the y value is 0 at smaller case y is equal to 0 or b. So okay, at any t. Alright, so our boundary conditions is all set. So now if we separate our variables, we easily get this equation. Now I hope you are already very much familiar of this. So we have already seen this in our earlier lectures, that from equation 3 we can easily get this equation 4. Alright, so now here we see some interesting stuff. So this is a function of x, one independent function. This is also another function y, and another independent function, plus some constant is equal to 0. So now once again we have to remember that both x and y, those are two independent variables and they do not have any relation with each other. So being an independent variable, so this derivative as well as this derivative, we can separately treat them as individual one-dimensional equation. Alright, so when we treat them as an individual one-dimensional equation separately x and y, so from our previous knowledge from the last lectures, we have equated them with some particular separation constant. So this time also I will equate them individually with some separation constant. So, and of course we knew that the separation constant must be a negative number. So arbitrarily I equate them with minus p squared here and I equate it with minus q squared there. So now we see we have three square quantities, they are summing up to 0, and this can only be possible at one condition. So automatic condition is that p square plus q square has to be beta square. So the sum of these two negative quantities has to be equal to the beta square. Okay, so negative plus positive should be is equal to 0. So from these considerations further we get two more sets of equations. Okay, so let's quickly erase the board and write those two equations over here and let's quickly solve it. So from the previous treatment, we get these pair of equations, and from our learned knowledge, we can easily solve these two. So we know that x is equal to, we can write a cos px plus b sine px, okay, and then y is equal to c cos qy plus d sine qy. All right, and so now we can solve these two equations further, means more specific solutions, by putting the boundary conditions. So the boundary conditions, once again, if you can remember that x this is equal to 0 and y this is equal to 0. So if we put that, so therefore we can easily get the specific solution. So we can write the specific solutions. So it becomes x is equal to a cos, sorry, because this part will become 0, so we will directly get p sine n pi a by x, and y is equal to d sine m pi by d y. Okay, so here we can see that these treatments give us the value of p is equal to n pi by a, as well as the value of q is equal to m pi by b. All right, so now we can actually equate our beta value with these things. So what was our beta value? So previously we assumed that beta square is equal to p square plus q square. All right, so now we can easily put those values in. So we can directly write, or of course we can write that beta square is equal to n square, or actually we can take the pi square part common, and we can write n square by a square plus n square by b square. Okay, so or we can directly write beta is equal to pi root over of n square by a square plus n square by b square. All right, so from this also we can easily find out the value of omega. So let's try to do that. The value of omega. All right, so the value of omega, okay, so we will come to that later part. So now this is the part of x and y, so therefore now this part is solved. Okay, so we know the answer. So let's quickly come back and get the equation for the time part. Okay, that means the function of t, uppercase t, in terms of time t. So let's quickly find out that. So coming back, I have already written the ordinary differential equation containing the time variable. So here you see that we can equate velocity multiplied by beta is equal to omega. Now we have already seen that the value of beta, it depends on both these numbers n and m. Okay, just we have seen a few minutes ago. So therefore, since beta depends on n and m, so we can call it that v beta nm is equal to omega nm. So it means that omega is now a function of n and m. So therefore, the above equation can be rewritten as this omega nm whole square t is equal to 0. So if we solve that, because there is no such boundary conditions, so we can directly get the solution as a general solution. So the general solution becomes t in terms of time is equal to, we get two new constants, and since those new constants will also be dependent on n and m, so remember the one-dimensional wave equation. So E and m cos omega nm t plus f nm sine omega nm t. All right. So this becomes our solution for the time function, the time dependent function. So therefore, we can now get the overall equation, which is u, x, y, and t. Of course, the general solution, the u function, would be dependent on n and m. So of course, we have to write the subscript n and m here is equal to of whatever we got previously. So that means f x y n m multiplied by t n m. Okay, so here also we can write n m. So now we can finally write the general solution. So general solution means, again we have to remember the concepts of one-dimensional equation. It said that not only the individual solutions for a particular value of n and m, any combination, that means the superposition or the summation of the different solution corresponding to different n and m would also consist or would also generate another solution for the entire equation. So therefore, we can write the general solution, that is the u nm x y t is equal to, it should be the whole the summation approach. That means we have n is equal to 1 to infinity, summation of m is equal to 1 to infinity, and u we write like this, u and m x y t. All right. So actually, this becomes our general solution for a two-dimensional membrane. Of course, we did not write the entire part UNM, so the UNM part over is here, so we can expand it. Okay. And all other concepts that were valid for the one-dimensional wave equation is also valid for the two-dimensional wave equation. Okay, so that means now we can talk about the first harmonic, second harmonic, third harmonic. So that means the fundamental, overtone, etc. Okay, so now we will going to take a look how a two-dimensional vibration can be represented graphically, means in terms of a physical picture. Okay, so that would be quite interesting. So let's take a look at that. So from the nature of the general solution that we just found, it says that like one-dimensional vibration, the two-dimensional vibration can also be a superposition of normal modes. So when we talk about normal modes, means we are having some vibration with corresponding to the numbers n is equal to something and n is equal to something. So here for 1D vibration we have nodes, right? But the nodes appear as points. Here in 2D, the vibration of a two-dimensional membrane, instead of nodal points, we should have a nodal line. Okay, so the nodes were zero-dimensional for 1D problem, and here the nodes are one dimensional for a 2D problem. So of course you know for a 3D problem the nodes will appear 2D. Okay, so before we go further, so let's assess the omega nm value. So omega nm can be written like this. So we have already found out the value of beta nm. So here, if A is equal to B, means if we have a square membrane, then of course this would be written as velocity pi divided by A whole root over of n square plus n square. Alright? So now, of course, this value is valid if A not equal to B. Alright. So now let's take a look at the different pictures of the vibration of a 2D membrane. Okay. So let's find out the fundamental one. Okay. So what corresponds to a fundamental? Of course, before I forget, we must mention that n is equal to 1, 2, 3, etc. Excluding 0, and the value m is equal to 1, 2, 3, etc. excluding 0. So I reckon the first fundamental vibration should be U11, where n is equal to 1 and m is equal to 1. So that means I can draw, so let's assume that for this 2D membrane, A not equal to B. Alright. So we have a rectangle, and so the rectangular plane is vibrating like this. Okay. Means the entire plane is going above its original resting plane and coming back. Alright. So now, so this we call as the fundamental U11. So what should be the second mode, right? So of course, keeping n is equal to 2 and m is equal to 1. So we can think about U21, where n is equal to 2 and m is equal to 1. So how it can be represented, alright? So that's the question. And of course, so that can be represented like this. Alright. So here I can draw a shaded plane like this. So here the vibration would something be like that. So if you think about this is the plane, so one part will go above, and one part will go down. So the vibration will be something like this. It will imitate some motion like that. Alright. So the thing is, what would be the next? Can we go to U22? But before that, let's take a look at a different scenario. So we have U11 and we have U21. So what happened when I just reverse the situation, that is n is equal to 1 and m is equal to 2. So what happens for U12? Okay, so for U21 and U12, whatever it is, what should be the omega value? So you can find it out that omega 21 is equal to omega 12. Since here what's happening is that the summation of n square becomes the summation of n square plus n square. Okay. So 2 square plus 1 square is equal to 1 square plus 2 square. So what we get is the two vibrations of exactly same angular velocity, means same frequency, but the modes are different. Okay, how the modes are different? So easily we can draw another mode, something like that. So now the vibration will be something like this. So we can call it U12. But both of these two vibrations are having the same frequency. So such kind of modes, okay, same frequency often means same energy, but their modes are different. So we call them as degenerate mode. Okay. So we call them degenerate mode. So in quantum mechanics, later we will find this kind of degenerate modes of vibration pretty often. So this concept of degeneracy actually arises right from the two-dimensional vibrating membrane. In the case of two-dimensional vibrating membrane. All right. So in next step, we can go for another mode. But the next question is, what would be the next degeneracy? Okay. So of course we can again write like U31 is equal to U13. The same thing will appear here. So in that case, you can easily understand that there will be two nodal lines, right? So we can explain or we can draw is something like that, okay, right here. So again, those two would be degenerate, okay. So from this lecture, as a summary, we can understand that the vibration of two-dimensional membrane is nothing different than the one-dimensional wave equation. It is just an extension of the one-dimension case into two-dimension. And secondly, the integers once again becomes very important, and the concept of degeneracy or the degenerate modes appear. So overall, this chapter gave us a nice foundation to study the actual quantum mechanics. That means studying electron as a standing wave. Of course, not in the physical, not in the classical domain, but in quantum mechanical domain. So we are ready to take on the chapter 3. So in chapter 3, we will be introduced to the most fundamental equation of quantum mechanics, that is the Schrodinger equation. Alright, so now we think we are ready to handle the Schrodinger equation. So we will see you in the next lecture. Till then, goodbye.